So welcome back. Our next speaker today is C S Unnikrishnan from the Tata Institute of Fundamental Research in Bombay. Unni works in experimental gravitation theory and laser atom interactions. His lab has been successful in producing a Bose-Einstein condensate in an optical trap. He has a wide range of interests, extending from the Casimir effect to cosmic censorship. When he's not playing his flute, which he plays very well, he's resting his hands on the pillars that support the edifice of physics, trying to test them for weaknesses. He likes to be provocative in his talks, and today you're going to hear him attack the foundations of motion and relativity.
I was really looking forward to this opportunity, and I thank Ravi and colleagues for the affectionate invitation to participate in RAD's 1000 Moons event. This talk is very important for me on two counts. One is that I'm talking to an audience which consists of my teachers, mentors, examiners, friends, friendly critics, and also great figures in physics and astronomy. The other important aspect is that the talk is prepared in a way which is my respectful offering to Rad. I've been discussing with him for over 20 years, ever since my student days. And as you know, when you try to explain something to him, your own clarity improves manyfold, and I have learned from that experience. Now, as the title suggests, I have to talk about something where I will advocate the need to change the very basis of theories of relativity and theory of motion. And therefore, true to the very theme of this conference, as the talk progresses, this very audience, friends, mentors, teachers, and so on, you will start developing a resistance to what I'm trying to say. And therefore, it will be sort of a live experiment on the theme of the conference itself. And this I find very interesting. It may go to the extent of people saying very nasty things to me at the end of the conference. However, I hope that, usually when I discuss with Rad, in his typical style, he will say, Ama, Apadiya, some words of encouragement. But here I hope to hear from him some stronger Tamil words of appreciation, not in the way Malayalis use them, but okay. So let me start. The basic theme originates from this observation. Physics in empty space is very different from physics in the presence of lots of matter. And that's what even general theory of relativity has taught us. However, fundamental theories of physics assume empty space as their backdrop. Universe with all its matter content and gravity existed ages before we started making our theories, certainly. However, all our fundamental theories of the physical world were completed well before we acquired any significant knowledge about the physical universe, its content, and its long-term evolution. So that's a fact. In particular, the theories of relativity and dynamics, as well as the theory of gravity, were developed assuming an empty universe. However, we know today that the gravitational potentials of the matter in the universe is 1 billion times larger than our local potentials in this very room. And if these have any say in dynamics, then we have completely missed that out in our theories. Therefore, a reconsideration becomes essential. And what are the results of such a reconsideration? That's the theme of this talk. And I would present to you empirical evidence. In fact, that is my strength. How would I dare to come and talk to you to such an audience that the very basis of physics has to be changed, my strength is empirical evidence. There is empirical evidence to reject the presently accepted paradigm for relativity, physical effects of motion, and the laws of dynamics. Now, let me give the context in slightly more detail. This is a very familiar picture of the microwave background radiation temperature from the Planck satellite, for example, which shows a map of the temperature on the sky of the microwave background radiation with fluctuations of the order of 1 part in 10 to the 5 tens of microdegrees, with an average temperature 2.7 degree Kelvin. Now, if you take out these fluctuations which we understand today due to gravitational potentials and so on, due to galaxies, what you get is supposed to get a smooth picture with average temperature. But the important thing about this is that the temperature is everywhere same in the universe, and it's monotonically decreasing. Of course, before this picture was produced, all these pictures were produced, there was another anisotropy known in this microwave background, which is called the dipole anisotropy, which is much larger, which is of 1 part in 10 to the 3 millikelvins. And the interpretation of that was known for over 30 years, which is that this is a Doppler shift of the radiation, since we are moving through the universe, the solar system and the galaxy and so on, at a velocity which is roughly 1 in 1,000 of the velocity of light, which is several hundred kilometers per second. So the universe looks anisotropic when you look at it. But that can be removed and you get this smooth temperature. Now, when you move through the microwave background, this allows you to determine your absolute velocity in exactly the same sense as we talked about absolute velocities in the days of ether, pre-special relativity days. So this is known. Any observer can determine whether he is moving or not with a sensitivity of sub-kilometer per second. And this uniform temperature serves as a universal time, which is same everywhere in the universe. You can synchronize your clocks in principle to this temperature locally everywhere in the universe, and there are no clock synchronization issues which are widely discussed in the physics of relativity. For example, the 1,000 moons of Rad could be stated at a particular temperature of the microwave background radiation. So every observer can decide whether he is moving or not, and all clocks in the universe can be synchronized to this temperature. And these two facts are important, though I will build up something which is more significant than this as we move along. Now, so the point is that massive universe is a preferred frame. There is one special frame, exactly one, apart from orientations, in which velocity, the absolute velocity is 0, where you see all the galaxies stationary, as well as a 0 dipole anisotropy. In all other frames, like this room, what you would see, either you can look at a dipole anisotropy of the microwave background radiation, or you can look at the galaxies directly. If you have the sensitivity, they would be all moving. And why is it significant? I will come to that later. So space is anisotropic in the frame of a moving observer. There is a large current of matter, which is a charge of gravity. You can immediately see how drastically different this is from physics in empty space. Empty space remains isotropic whether you move, if you move through it. But the real space, the once given universe, don't behave like that. Now, a quote from Planck: the gist of the principle of relativity is the following. It is in no wise possible to detect the motion of a body relative to empty space. In fact, there is absolutely no physical sense in speaking about such motion. If therefore two observers move with uniform but different velocities, then each of the two with the same right may assert that with respect to empty space, he is at rest. And there are no physical methods of measurement enabling us to decide in favor of one or the other. This, of course, is gone. Einstein's opening sentences in his 1905 paper: it is known that Maxwell electrodynamics, as usually understood at the present time, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. Depends only on the relative motion of the conductor and magnet. This is what we think, okay, which is more or less true. Examples of this sort, together with the unsuccessful attempts to discover any motion of the Earth relative to the light medium, suggest that the phenomenon of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest. This defines the standard paradigm of today's mechanics and basis of all physics. And there are various ways of saying it. Phenomena of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest, and that can be shown to follow from a hypothesis that the speed of light relative to all uniformly moving observers is an invariant constant, which is a basis of special theory of relativity, which distinguishes it from other theories of relativity which existed at that time, notably the Poincaré-Lorentz theory with ether. All uniformly moving observers are equivalent to observer at rest, and so on. Now, I want to ask this question. Is it really true that phenomena of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest? Is it true that the relative speed of light is an invariant constant? How do we know that? Are there sufficient experiments? Have you looked at experiments? All this I want to examine in this context. Now, let's look at what we understand about familiar waves, waves in water, sound waves, and so on. Suppose there is a wavefront which is emitted at some point, and suppose there are observers, somebody standing right at the point where it was emitted, and there are other observers moving relative to him. As the wavefront expands, the observers are moving, and you can immediately see that the wavefront is at different distances from these observers who have moved. Of course, for the observer who was at absolute rest, the wavefront is isotropic in all directions, isotropic distance. Whereas for all other observers, of course, the distances depend on the direction in which you look. This is precisely why we say for these familiar waves, the relative velocity is not isotropic. It depends on the velocity. There are first order corrections, v minus c, v plus c, and so on. This is what we propose we have in our present theories of light and relativity. So let me show it. It's exactly the same experiment if you do with light. The hypothesis, nobody has done this experiment, but the hypothesis is that this is what you would see. For each observers, their own light sphere, what I call many worlds in optics. So this is not part of our experience. This is exactly what special theory of relativity puts out as a hypothesis. For every observer, it's isotropic. Therefore, an invariant constant. Isotropic with the same radius. So let's examine this. So there is one observer who is at rest. There is another observer who moved away from that point. And we have this isotropic light spheres. So Einstein's special relativity asserts that the relative distance traveled by light for each of these observers is identical in all directions because the relative velocity of light is an invariant quantity. So therefore, if the relative velocity is invariant and same, the relative distance traveled is also isotropic, independent of the velocity of the observer. Is it really true? Is there any experimental evidence for this picture we have today for relativity? And what's surprising is that there is no empirical proof of this whatsoever. There is absolutely no experimental evidence for this hypothesis. There are many things which are consistent with this, but that doesn't prove that this is really true. So we have to examine, because I see many people being surprised at this statement that there is no empirical proof for the very basis of special theory of relativity and essentially all of physics. So we want to examine this. For that, we want to look at two-way propagation of familiar waves, because most of the experiments are done that way. So these are just familiar waves. These experiments can be done with sound waves or water waves and so on. So waves are generated here, sent in two directions. There are mirrors here. So this is some reference system. So if you send these out these two waves in a system which is at rest, they will reach the mirrors at equal times. But if you are in a moving system like this, of course, by the time one of these waves reaches the other mirror, other one has reflected and reached considerably back to the observer. This is our experience with familiar waves. And you might think that if you continue with this experiment, keep moving, this will reach, of course, earlier than that. But that's not what happens. You continue with the experiment, and very interestingly, both waves will come at the same time to first order in velocity. So, two-way measurements hide one-way anisotropy. You can never measure a one-way anisotropy in the velocity of waves with a two-way experiment to first order. There is a second order correction. So wavefront reads back simultaneously, as in the case of an observer at rest, if you are looking at only first order effects. Of course, there is a second order effect, which was the basis of the Michelson-Morley experiment. So let me calculate that second order effect. One way, when it is going out, it is L by L is the distance from this to that mirror, is L by C minus V, because that's a relative velocity in the old picture. Or for familiar waves, there is a first order Galilean velocity for the waves. So L by C minus V. When it comes back, you are catching up with the wave, so it's L by C plus V, and it is 2L by C with a second order correction. So this is the time different, two-way time, which you will measure for a wave which is sent back and reflected back. There's only a second order correction. So Michelson-Morley experiment is some such experiment where you look for a second order correction which is different in different directions, perpendicular arm and this, and that's the Michelson-Morley experiment, so interference experiment. And this is a signal they were looking for. This is on this arm, which I just showed you on the previous slide. This time difference is on the perpendicular arm, which can be calculated, and the difference is only in second order. Now, what was the result of this experiment? This was the signal they were seeking, and no signal was seen. Delta T was 0 essentially. The phase difference was 0. It did not depend on the velocities. Whereas here there is a second order dependence in velocities. This signal was absolutely 0 in their experiment, within the errors. Now, there was the famous Lorentz Fitzgerald hypothesis. It says either theory is okay. There is a special preferred frame. Velocity of light is anisotropic. It has a Galilean behavior. However, the length contracts. This length, L parallel, contracts in motion by a second order quantity. Perpendicular, it does not contract. And therefore, you will see that if L parallel has this second order correction, both these terms are exactly the same. You will get 0. So that's the Michelson-Morley experiment explained away by Lorentz. So anisotropic length contraction cancels the anisotropic speed of light. Now, Einstein's view, there is no real length contraction, no preferred frame, no contraction, but isotropic speed of light. So that's another solution to the problem, because all the second order corrections are not even there to start with in Einstein's theory. So therefore, this difference is always 0. Both these are explanations of the same experiment, and all two-way experiments ever done in physics in this field can be explained by both of these. That's a fact. There is some misunderstanding in the literature about it, but I have examined them with great care. All experiments done to date, all of them can be explained either this way or that way. Okay, that's the experimental situation. Therefore, there is absolutely no proof of stating this. So, if you look at historically, about that time, there was this theory which was successful in certain ways. This theory was advanced. What just happened? Not because of a forced by an empirical proof. Sociologically, it just happened that most people went to that. Very small fraction of people working still on this. So, how do you settle between these two kind of theories? The only way is to do one-way measurements. There's no way we can settle this with a two-way measurement. You have to look for a first order anisotropy, which cannot be cancelled out by a second order effect like length contraction or time dilation. So that's the crux of the matter. So I need to go into certain illustrations so that the ideas are, many people here, you don't need these cartoons, but I prefer to do it this way for clarity. I have also digitized the propagation to mean that 1 unit of time something propagates 1 unit of length if the velocity is an invariant constant. This is easier to think, but all this can be formulated in a continuous manner. So if you are a stationary observer, as time progresses, you would see propagation which goes some distance, 15 units for 15 units of time or something like that. But in your moving frame, special relativity says it still moves the same distance relative to you, relative to the observer, relative to the moving observer for the same duration of time. Light moves exactly the same distance. Whereas in the absolute frame theories, the situation is of course different. It cannot move the same distance, it will move a shorter distance. That is precisely why, dividing this distance by time, we say that the relative velocity is smaller. So we have to somehow distinguish between this situation and that situation. But there's a difficulty with this. How do you do this kind of experiment? To do these two experiments, you need a clock there and you need a clock there. You have a starting clock here, but how do you know when this entity reached the other side? You need a clock there. And there is no way to synchronize this clock independent of theory. Either you have to synchronize clocks here and move it there, you need a theory of time of moving clocks. If you want to send a light signal from here and synchronize the clock there, you are testing what you are using what you are going to test. So it becomes a circular argument. So this is no way of doing this experiment. But you know that you just want to measure the relative speed, how much distance something travels in a given time. There is a very, very simple way of doing it. It is to fold back this path on itself. We do it all the time actually. You need only one clock. The entity can move. It's exactly the same entity which is folded back here. If you think a little bit about this, I don't want to go into great details of this logic here because of lack of time, but we can talk about this logic in great detail. And the point is that you will measure exactly the same time for the same distance as in these experiments if you just fold it back here. And you can also have a moving observer here, as I will show in the next slide. So, for example, Earth's speed around the sun can be measured by just when it comes back again to the same position, you know how much time it has taken, the radius and so on. So now let's look at how to do such an experiment. It's essentially a comparison between how ordinary waves behave and how light behaves, because that's a real question. Now, if you do this kind of an experiment, sending light waves around a stadium kind of a thing like this, and sending waves, familiar waves, around a folded path like this, and look for the time it takes for it to reach back to the observer, a moving observer, what you would see is the following. You would see that they will not reach back at the same time because the relative velocity in two different directions are different. That's the interpretation of this effect, that you don't get back them in the same time. If the relative velocities were exactly the same into two different directions, the relative distance from this observer at all times will be equal in both directions. Therefore, they have to reach back the observer at exactly the same time to first order. Whereas, if you do this experiment with sound waves, water waves, and the Maxwell-Lorentz light, old light, this is what you would expect to get. This is what you get for these familiar waves. Therefore, you can compare this experiment with what you get for light. You generate light instead of other waves, and if relative velocities are same, relative distances are same for the same time, they should reach back at the same time. And this can be done as an interference experiment. And note that the observer is moving inertially. That's the point of making this a stadium-like structure and not a rotating SANAC. But idea is very similar to SANAC. In fact, SANAC published this paper with the title Demonstration of the Ether by a Rotating Interference Experiment. Anyway, so that's the way to do this experiment. And we have done some preliminary versions of this experiment and we are trying to do better. Essentially, the experiment consists of an observer on a frame in which you generate light with a laser, split it into two parts. The detector is also on the same frame. This frame can be moved back and forth at some particular velocities. They are not very large velocities, sub-meter per second. Then you have the stadium path, one-dimensional path. It's exactly the experiment which I showed in the previous graph, now done with light. And you look for a fringe shift. You get fringes on this detector. You can look for a fringe shift as a function of velocity, like Michelson, but this is a one-way experiment. Things don't come back to the same point by returning back, but by looping around. And this is the result of the experiment. This is the time difference, which is essentially the fringe difference divided by the velocity of light as a function of the velocity. And you can see the first order anisotropy here, V by C. Is here. D by C is the time taken, V by C is anisotropy, this one here. It shows very clearly that relative velocity of light has a first order anisotropy exactly as Lorentz, Poincaré, Maxwell and those people would have imagined and expected. This is what special relativity would have talked about. I want to present more evidence, so we can come back to this in discussion if you want. Another experiment, it's a one-way experiment. Suppose you generate pulses of light here, some marker, some comb, which you can send from here to there through optical fiber or free space. There is identical atomic clock on the other side, which runs at a similar, more or less similar rate, which can also generate a similar comb, let's say 100 megahertz or something. This comb can be sent to the other comb, and you can compare the phase difference between these two combs. Of course, such a phase difference depends on a lot of factors. There is a propagation delay, electronics delay, all kinds of delays are there. However, so there is a delay between these two combs when it reaches there, an arbitrary delay, which depends on all these factors, clocks, initial synchronization errors, everything. Except that the important thing in special relativity, if this frame is moving, in special relativity, light takes exactly the same time from here to there, whether moving or not. Therefore, the propagation delay is a constant in special theory of relativity. So this phase difference should not depend on the velocity of the frame in special theory of relativity. Whereas in a normal preferred frame theory, if the frame is moving, it takes more time for light to reach here because the clock has moved out. Therefore, the phase will depend on the velocity if the velocity of light is not an invariant constant. That's one effect. There is another effect. The only way to change velocity of a frame is to have an acceleration. But if you accelerate with two clocks in a frame, they cannot run at the same rate. So you can calculate how much this clock will delay relative to that clock if this frame is accelerating forward. General theory of relativity has a very simple expression for that. Just equivalence principle is enough. You don't even need a full theory. And that effect, if you calculate, you get exactly the opposite. In fact, it's a device which Einstein used to derive certain results anyway. So this clock will delay compared to that clock by some amount, which means the comb generation has a pullback. I shouldn't use this word in an audience with a lot of mathematicians, pullback. But so the phase difference, which depends on the one-way propagation of anisotropic velocity of light, gets cancelled out by the clock delay. Whereas in special theory of relativity, this effect is there, but that effect is not there. So the time-dependent phase is expected if special theory of relativity is correct. No phase difference should occur, a null experiment, if special theory of relativity is not correct. And people have done this experiment, not with the right interpretation though, but this also we can discuss later. I just want to show the result. Now, how much is expected? Even if you put the velocity of the Earth around the Sun, just 30 kilometers per second, and calculate this, you will get, here the velocity is not what I mean. This is just the distance between this point and that point, 30 kilometers. You need to put a velocity, how much change in the velocity to calculate the time shift. You can either put the velocity of the Earth around the Sun for such experiments, or you can put the velocity of the whole system, how much the velocity changes, taking into account that the whole system is moving through the cosmic frame at 10 times more velocity. So you get numbers which depends on the model, and here are the results of such experiments. You get a delay which is much less than 1/100th of what you expect if the velocity of light was anisotropic. So this is another evidence which clearly shows to me that light behaves like ordinary waves. It is Galilean. So I have reliable experimental evidence that the relative speed of light is not an invariant constant. It is anisotropic to first order in V by C. And then you can ask the question, what about Lorentz transformations and invariance of Maxwell's equations and so on? I'm pushing a Galilean view here. Miracle. So now let's look at that question. So this is a situation where there is a light front which is expanding. there is an observer which is moving, and in a absolute frame kind of a theory, you would have said that since the distance of the wave from the observer is smaller for the same time, the relative velocity in this direction is smaller, relative velocity in that direction is larger, just the Galilean corrections. So this is the distance traveled. In this direction is larger, the distance traveled in this direction is smaller, because the relative velocities are proportionately that way. Now, so that is a velocity calculation, just the distance divided by time. You get c minus v in this direction or c plus v in that direction. However, we can make the relative velocity isotropic on paper if we use blatantly unphysical clocks, one for each direction. Suppose I just claim that the clock here runs differently from the clock here. For example, I can say that this distance is smaller, but the time here has also progressed only a small amount relatively. Therefore, if I make such a proposal, the distance divided by time can be made a constant. I can tune it. For example, if the forward time is defined as t1 minus v by c, and the backward time is defined, so the clock here runs only that much relative to a clock here, and the clock backward runs only that much, I would immediately get forward and backward velocities c. You would not recognize this as a Lorentz transformation, but I assert now that this is the first order part of the Lorentz transformation. I will go into this again. So these two equations, you need two equations because you need two different clocks. They can be combined into one equation by just making this sign of the direction apparent in this product, Vx by c square, because x, which is the distance from here to that point where you are considering, is just c times t for this one-dimensional problem. So you see, this is a major part of the Lorentz transformation. There is a second order correction which we can take care of, but I don't want to go into details. So let's look at this in a slightly more general sense before we progress. So if in this problem, the observer has moved here to any point on the wavefront, there is some distance d prime in that frame, in the moved frame. In the rest frame, it is c times t here, and so on. No, so distance to wavefront d prime is anisotropic. Therefore, if we define time at d prime equally anisotropically, just define distance is equal to time, then trivially the ratio is a constant. This unphysical anisotropic transformation of time is the Lorentz transformation. Physical time has no first order anisotropy. So let me show that to first order. I can do this for second order also. D prime is essentially Ct minus Vt cos theta, which you can check. So there is a cos theta factor which comes. Define time at t prime, time t prime at d prime as just d prime by c. It's a definition. Then d prime by t prime is c, trivially, right? Everywhere, independent of the d prime. And that t prime, you can see what it is. It is just this. Since x is cos theta, this is the angle which I mean. Cos theta is x divided by ct, you get the Lorentz transformation. So that's the first part of Lorentz transformation. Of course, such clocks are inconsistent with the FRW universal time and CMBR and everything we know about clock synchronization. Once you can prove it as a theorem that if there is one frame which allows you to allows a universal synchronization, in all frames you can do universal synchronization. So Lorentz transformation is a trick on paper which makes the velocity of any waves, light particularly, isotropic on paper by this first order transformation on time. Usually you don't think of time as an anisotropic quantity. Space is a three-dimensional space, can be anisotropic for a moving observer. You make time anisotropic, the division becomes isotropic. So of course with those transformations, you know that immediately x minus ct and x plus ct are invariant. So the general solution of the wave equation is invariant under this transformation. This was shown by Voigt in 1887 already. The second order correction can be put on the y-coordinate or the x-coordinate, but for physical consistency we nowadays do it on x because that's what is experimentally valid. Okay, so this remains invariant, but it has no implication that the physical relative velocities are invariant. This is a problem. See, Lorentz did not insist on the invariance of the physical velocity of light. He had the Lorentz transformation, but he had the ether theory. If you now with the either theory and the Lorentz transformation, if you suddenly say the physical velocity of light is an invariant constant, there is a big inconsistency. Einstein went ahead and announced this as a physical property, and that's the problem. Now I want to give other evidence. So I want to now quickly go to some other evidence, which is very important. Time dilation, which is frequently measured in experiments with greater and greater precision. It's fairly easy to measure even in a student experiment these days because muons are available. So all physical phenomena appear to slow down by that second order factor when in motion, and it's symmetric in relativity. No interaction is involved. So it's in some sense a mystery. Usually a physical change you would like to attribute to a physical interaction. Here there is no such thing. You move, clocks slow down for some reason. First of all, space is not empty, and this important aspect of special relativity is not testable rigorously anyway. Because if you construct a theory in empty space and insist that empty space is required for the test, you can never find it. However, consider this calculation. This is just a representation of the universe up to some distance, just about few gigaparsec. Of course, the universe is much larger. We know the average matter density on the universe is about that quantity. So matter up to a distance of say 3 gigaparsec or so generates a gravitational potential in this room, which is very large. You can just calculate the gravitational potential here due to all this matter, which is 0.4 times c square. Perhaps you know that if you consider all the matter in the universe, the Newtonian gravitational potential, at least naively calculated, is numerically equal to the square of the velocity of light. This is already very remarkable because if I replace all Lorentz transformation formulae, the gamma factor, the c square is replaced by the gravitational potential of the universe. Nothing phenomenologically goes wrong. It's a consistent phenomenological theory, experimentally valid. But anyway, I don't want to go into that. We know that if there is some matter up to some distance, it creates a gravitational potential here. Of course, just with this gravitational potential, a clock will run slower by 40% compared to a clock in empty space already. Okay, but that's not the point I want to say because all clocks will run slow, we cannot compare them and so on. What I want to say is that now consider motion in this universe in the presence of all this matter. Gravitational potential in relativistic theories don't remain a constant in a moving frame. You start with a potential, like in electrodynamics, you move, there is a V by C correction, which is a vector potential. There is a second order correction to the 0th time also. So you get additional enhanced lifetime. So you look at the experiment where a muon is coming, you are measuring the lifetime. You will see that 40% additional enhanced lifetime compared to what is predicted by special relativity, even if we consider only matter up to 3 gigaparsec. This calculation can be easily done. Anybody can do it, Newtonian, but you can do it more rigorously. But this is not seen. Muon lifetimes have been measured to much higher precision. You don't see that additional correction. So the only way out is to say that there is no special relativistic time dilation. Everything comes from the matter in the universe, not 40%, all of it. Then you don't have to talk about a correction. Okay? And this is another evidence which I want to bring in. Again, we can discuss in detail. Now the case of asymmetric clock. It's a well-known phenomenon, but people have not looked at it very carefully. We know special relativity talks about time dilation. So if you have a laboratory clock and the two other clocks synchronized with this, moving in opposite direction, let's say, at equal relative speed. Special relativity says there is time dilation for both these clocks relative to that clock, equal time dilation. Now special relativity says, suppose this frame is moving, this laboratory is moving, and these two clocks are moving exactly the same way, something like this. Special relativity say, if you do this experiment entirely within that frame, relative to this clock, this will have the same time dilation, that will have also the same time dilation. Nothing changes. It is as if the frame were at rest, the entire results of special relativity. But of course, in an absolute frame theory, this clock is now moving. It's not a stationary clock anymore. And this clock is moving even slower, that you can see here. This clock is moving, the frame itself is moving, so the actual velocity, absolute velocity of this clock is less than the velocity of this clock relative to the preferred frame. So absolute frame theories predict that this clock will not have a time dilation. In fact, this clock will have a time dilation relative to this. And that clock will have an even larger time dilation than what is predicted by special relativity. That's what an absolute frame theory will say. And anybody who is familiar with GPS data know that every westward clock transported runs faster than the laboratory clock. Not slower, it's always faster, which is this effect. And usually people who analyze this experiment within special relativity take the convenient way out of going out of their frame. Of course, then it is an absolute frame theory, naturally, because you have gone out and say the frame is moving. Again, you can check these evidences, but this is a fact. Every westward clock runs faster than the laboratory clock, because Earth is moving the other way. It's exactly like this frame. So experiments do show that the relative rate of clock depend not on the relative velocity, but on their absolute velocity. Now I want to quickly say something. How much time do you have? About 10 minutes? Or?
2 more minutes.
2 more minutes. Can I take?
20.
Okay. Can I take a little bit more?
Time doesn't.
Huh? No, one more evidence from electrodynamics, because Einstein paper started with this example. This is a magnet and a wire which can be moved, conductor which can be moved. So let's look at this example, a wire moving over a magnet. Magnetic field is uniform. Maxwell's equations don't help in calculating what the current is. You need the Lorentz force law. It's a force on the electron, free electrons, by this equation. Now what is this wave? Einstein asserted that it is the relative velocity between the magnet and the wire. Similarly, if you take a disk magnet and move a wire, you get exactly the same result essentially, except that you have to integrate that E over velocities are dependent. Now you can do the reverse experiment. You can move the magnet and current flows, and this is precisely what Einstein pointed out. It's a symmetrical phenomenon. Now Faraday did some experiments early in which he did something with a circular manual like this. There is no current in this example. There is a relative velocity. There is absolutely no current. Going further, if you move the whole thing together in this Einstein example, of course there is no current. People will say it's because relative velocity is 0. You can move these two things together, there is a current which flows. This is a unipolar homopolar induction, well known for electrical engineers. You will never find it in a physics textbook, except some Russian textbooks. So, phenomena of electrodynamics as well as mechanics do possess properties corresponding to the idea of absolute rest. Hence, a new basis of relativity, mechanics, and dynamics is required. I call this paradigm cosmic relativity, and I want to run through what that paradigm is. I don't want to go into details because again we can discuss. The point is this: in all frames which is moving, there is a large current of matter, which is a charge of gravity, and this current will produce potentials. So cosmic relativity says gravitational potential due to all the matter in the universe depends on whether one is moving or not, and there is a vector potential apart from the familiar Newtonian potential. All this can be put in the language of metric. These together are the cause of all relativistic phenomena, including time dilation, length contraction, limit on the speed of propagation itself. Also, cosmic gravity determines the law of motion, Newton's law. I'll just immediately show it in the next slide. And the principle of equivalence and its direct consequences. Okay, that's why I want to call it as a paradigm. Let's not worry about this. But I want to say that what you have to start with is not empty space, space with matter, which is a Robertson-Walker metric, and you can do a Galilean transformation on this. In fact, if you do Galilean transformation on Robertson-Walker metric, you get isotropic metric again, which is not consistent with the space you see when you move, which is anisotropic. Anisotropic space, anisotropic matter current, anisotropic energy momentum tensor, but isotropic metric, that is not nice. So you do a Galilean transformation and you get these off-diagonal elements here, which is the gravitational potential, the vector potentials. And with these, if you calculate how much, what is the time and space relation in a moving frame, you get back length contraction and time dilation. There is no difficulty. So Galilean transformation plus gravity of matter field universe gives the correct relativistic effects on clock and scales. That's all you need to check any experimental evidence. It does more. Look at this vector potential. It is V by C multiplied by the other part. Now you see, if you are moving through the universe, you get a vector potential. But if you are accelerating, v is time dependent, you get a time dependent vector potential, and we know that time dependent vector potential is equivalent to a reaction force. You can write that equation. It's just a Faraday Lens law, but written for gravitational potential I am writing. Now you see, this is acceleration, and that quantity, suppose we call inertial mass. This is, I'm just repeating Siama following Mach. You get Newton's law. You need a force to accelerate something through this universe because you have to overcome a time-dependent vector potential. You have to overcome the gravitational potential generated by all these galaxies. Newton's law is a consequence of cosmic matter and its gravity. It is a relativistic law and it's a magnetic law, like Lenz's law. Okay, gravitomagnetic. Of course, the next step is trivially follows. Mi by mg is just a property of the universe. It's a gravitational potential of the universe. No wonder it is a universal ratio. Okay? And it has a very interesting consequence, which I will state, I will not prove this. Usually equivalence principle experiments are done by dropping two things like this, and you look for a differential acceleration. And you would say that this is acceleration of 1, that's acceleration of 1 because there's an inertial mass in the denominator. Usually you say this ratio is universal, which is what I showed. But if G was material dependent and long range, you would say equivalence principle will not be valid. If G is material dependent, these accelerations will of course be different. You know university of free fall in the conventional picture. But look at it, this cosmic gravitational picture. This is not just falling like this, it's falling in the presence of all this matter. So in the inertial mass itself, the coupling constant comes in. So the ratio of gravitational mass to inertial mass is still a constant, even if gravitational coupling is composition dependent but long range. That's a remarkable result according to me because it goes beyond the premise of general theory of relativity. And in a rotating frame you can calculate all this. There's a curl of this gravitomagnetic field, and it trivially gives a gravitational Lorentz force, V cross B, which is the Coriolis force. That of course people have already said, following Mach, Siama and so on. So this is all known. So we are at the end of it. There is empirical evidence, reliable empirical evidence that relative speed of light is first order anisotropic. There is enough evidence to assert that all relativistic effects, I should have said, are gravitational effects of the causally connected entire matter in the universe. Therefore, a paradigm shift in which the gravitationally dominant preferred frame of the matter-filled universe becomes the basis of relativity and laws of motion, replacing completely the empirically invalidated theory of special relativity. This is natural and unavoidable. The earlier this is done, the less embarrassing it is for physical science. Also, I don't have confidence that I will complete 1,000 moons. Okay, so I would like to see it much earlier. Cosmic relativity, no less will do, and no more is required. Thank you.
See, 105 years after special relativity, at that time Einstein could possibly envisage the scenario that which is at the base of your thing. So going back to sociological preference of Einstein's theory to Lorentz theory that you referred to, what is the current sociological reaction to this? Because the arguments you give...
I would like to ask you this question because
but
sociology is from that side.
But you have given talks in very honored meetings like Marcel.
It's very interesting. I have been okay, only now I have a complete picture in terms of empirical evidence. When I started off, I had some evidence. For example, I didn't know about this asymmetrical clock, though it was a very famous result, and I should have known it. I didn't know till I predicted it from within this, and I was going to give up. I mean, I thought that never happens. Then I found these evidences, and I was quite happy about it. And I have given lots of talks, about 50 or so in the last 3-4 years on this topic. There is a lot of friends allow me to talk about this in conferences, especially in Europe, because the people who do clock experiments in the Paris Observatory and so on, they are just generous and benevolent, but they criticize when we are drunk, Otherwise, not much happens. They don't believe it. Now, the only significant thing I want to say quickly is that I tried to get it refereed in the proceedings of the Royal Society. I had a tough time. Finally, after some appeals and so on, Anthony Huish took it up because I complained to him that something is not proper. Because both referees said publish it and it will replace special relativity, and the editor refused and he wouldn't communicate with me. Finally, Herman Bondi looked at it. He said, I'm just too old to gauge what's this, and I had to give it to a junior colleague. I don't believe it is plausible. But then I wanted to communicate with him, but within 2 months he died without knowing a fundamental truth of nature. But okay, that's it. And after that, I didn't try very hard to publish because I wanted to complete all empirical evidence. In fact, I'm doing that first experiment which I mentioned. I'm trying to do a second experiment. Now femtosecond lasers are much better, much cheaper. This to comb transfer and so on. So I'm trying to do all this so that once I have the strength of empirical evidence, nobody can touch me. And that's my confidence. It's exactly what Professor M.G.K. Menon, quoting Buddha, and Shankara himself said. If there is evidence, no theory can be brought against it. See, there are two aspects. One is looking at absolute velocity, time definition and so on. But the physical effects in this theory comes from a physical interaction, gravity. And that crucially depends on how large the potentials are. Now there is an issue here. There are certain things which are given to us a priori, like the universe. We don't know why the velocity of light is at particular value. If that is linked very strongly to the potentials, maybe the potential was something different. If the universe had only neutrinos, maybe the velocity of light also could have been something different with the ratio, 5 by c square being the same again, 1. Could have happened. But the present understanding is, the way I understand it, you need critical matter, critical density for this to go through, and that's a very nice thing anyway.
Well, the last part of your talk where you basically proved Mach's principle, I think that seems okay to me. But
if that is okay, you continue.
But the fact that you do not want to see, as far as I understand from your talk, that you do not want to see C as a universal constant of nature.
It is not an invariant constant relative to moving observers as asserted in special theory of relativity.
Yeah, but then you throw away all kinds of things which follow
don't.
from special relativity.
No, you don't. All those things follow from Lorentz's relativity is my claim. All those things.
Even
equal to
Dirac's combination of quantum mechanics and special
Yes.
relativity giving antimatter and all these
Yes,
type of
because
things.
all you need is the transformation on time and space, the second order part. That is all you require for all those equations. There is no experiment at all in the whole history of physics where anything more is required from relativity.
I have to think about whether I can follow that. But,
Especially these first order corrections are not required at all.
I
It's not
cannot,
there. Time dilation and length contraction, all what is required.
But C must be a universal constant of nature. All of our
I have
physical
given
laws
you
collapse.
experimental evidence that it is not. Now, can you say it must be? No, it does not. It does not.
Yeah, sorry to interrupt, but perhaps we could continue later. If I could very a question, and then after that.
What about precession of the perihelion of Mercury and, for example, the very precise measurements of time delay of signals passing close by the sun and coming back?
Yeah.
Can you reproduce those very detailed agreements with
Yes,
experiment?
yes.
And if so, how do you do it?
Yeah, see, here the issue is what is the basis. basic theory. What this replaces is special relativity. Now you can ask the question whether general theory of relativity is consistent with this completely. It is, except for one point. So let me show that this slide. Now, whatever equations we write in physics, or Hamiltonians we write, all this should have considered all the matter in the universe. That interaction is there. In fact, these Hamiltonians will contain these constant terms which are very large. It may not affect most aspects. Now look at Einstein's equation, which is written down in this universe. My claim is that the original equation, which does not have this term, it is just these two equal to some energy momentum tensor. I am saying it needs a permanent correction. It needs a small permanent correction, which is the TIK of the universe. Since it's permanent, I am putting on the left side with the same coupling constant. The importance is that, of course, for terrestrial experiments, this is not important, because TIK of the universe corresponding to the density of 10 to the minus 29 gram per centimeter is a small quantity compared to this for terrestrial experiments. So all those questions which you asked will go through even without this correction. But this correction is essential if you want to take off the limit of general theory of relativity and reproduce all the results which you see for time dilation and things like that. So vacuum Einstein's equation as normally written is Rik is equal to 0. That is incorrect. It's an approximation. You need to write it like this. There is no vacuum Einstein's equation in that sense, because there is no vacuum. Universe is a priori, it's there, given, and this equation was written ages after all this was there.
Last question from Bernie.
The answer to this, I think, depends upon a quantitative question that I'm afraid I can't do in my head right now. But the evidence is very good that out to a redshift of about 5, the fine structure constant is constant.
Yeah.
And furthermore, that the ratio of the mass of the proton to the mass of the neutron is constant. But let's concentrate on the fine structure constant. Now, the fine structure constant involves H and C.
Yeah, but C is what? I can say it's just the gravitational potential of the universe.
So it's constant to some fraction of a percent.
Yeah, but that C does not have the interpretation that is the relative velocity of light with respect to a moving observer.
It has to do with
It is some
electromagnetic
constant, it's some
equations
scaling.
and Maxwell's equations, and therefore it has to do with the
No, so
velocity
I
of
showed the
light.
Maxwell's equation, how they are made invariant on paper by the Lorentz transformation. There is no inconsistency at all with all this. Absolutely nothing.
So the,
All those are intact.
anything that
Exactly as all this would have been intact if the Poincaré-Lorentz theory continued, except that you would have had this concept of an ether floating around. All I'm saying is remove the concept of ether, replace it with cosmic gravity and the cosmic frame and its gravity. Everything goes through. Everything.
I can't
Except-
comment.
so
I
that
cannot
should be-
comment on that. Just
So I
freeform
would really like to see counterexamples which are valid. Then
well,
I can look at them.
I-
But
I-
all I have done so far is to look at over 100 experiments and analyze them in great detail.
Have you received comments from some of the heavies?
Some of the heavies are here.
No.
No, I have got criticism. For example, I have been discussing with Rajaram, who in the initial days when things were nebulous, which helped me a lot because he is unforgiving. He attacks. But he has been friendly. He has been my teacher. And so I have refined a lot of things, and I like those criticisms. And going above criticism is this process which has brought me here.
I have a question. Could I have a copy of the paper?
Yes.
That's all.
Yes.
I'd
Yeah,
like to show it to one of my young
They are
friends.
scattered in various places, but I will give you. At least this probably something like that.
Well, let's thank the speaker. I think we
There's a very old version which I should replace with all this. But
should move on and we can discuss over lunch.